Welcome dear students to a very important topic related to the chapter chemical bonding, and that is about the bond angles. Before coming to the main topic, let us first discuss the difference between molecular shape, molecular structure or molecular geometry and electron pair geometry. Dear students, first of all, keep one thing in your mind that molecular shape, molecular structure, and molecular geometry, these three are the same things. They are synonyms of each other. And whenever there will be written molecular shape, molecular structure, or molecular geometry, it means the arrangement of atoms around central atom. So when you will be discussing the molecular shape, you will be looking at the arrangement of atoms around the central atom. But when you are talking about the electronic geometry, my dear students, electronic geometry means or electron pair geometry means the arrangement of electron pairs around the central atom, and that arrangement will include both bond pair as well as the lone pair of electrons. So arrangement of both bond pairs and lone pairs around the central atom, that will be called as electronic geometry or electron pair geometry. So both these, they are different from each other. Molecular geometry is something else and electronic geometry is a different concept. Molecular geometry involves the arrangement of atoms around the central atom, and electronic geometry involves the arrangement of the electron pairs around the central atom. Now let us come to the main topic, that is the bond angle. My dear student, bond angle is basically the angle between any two atomic orbitals that contains the shared pair of electrons or bonding electrons around the central atom. So angle between any two orbitals having shared pair of electrons or bonding electrons around the central atom in a molecule or complex sign, that is called as the bond angle. Bond angle is measured in degrees by using different spectroscopic techniques, and there are three main factors that decide the bond angle in a molecule. One of them is the hybridization of the central atom. Second is the number of lone pair of electrons that the molecule possesses, and third is the electronegativity and electronactivity of both central as well as the peripheral or terminal atoms. Bond angle is directly related to electronegativity of central atom. So if the central atom is more electronegative, its bond angle will be greater. But bond angle is inversely proportional to electronegativity of peripheral atom, which means if the electronegativity of peripheral atom keeps on increasing with the same central atom, then the bond angle will be decreased. Similarly, bond angle is inversely proportional to number of lone pair of electrons. If the lone pairs they increase in number due to the greater lone pair repulsion, the bond angle will keep on decreasing. So these are the relation between the bond angle and the electronactivity of central and peripheral atoms, and the relation between the bond angle and the lone pair of the electrons. Now let us consider different hybridizations in which there will be different bond angles. First is the sp hybridization. You know, in sp hybridization, the molecular shape as well as the electronic geometry. So molecular geometry and electronic geometry, both they will be same, and both of them that will be linear. Look at this please. If you will see the arrangement of the bond pair of the electrons, for your convenience, I am removing these atoms from here. Just look at the arrangement of the bond pair of the electrons. The arrangement of the bond pairs is linear. So electronic geometry is linear. Now look at the arrangement of atoms around the central atom. So I will be writing down here atoms. And now the arrangement of atoms around the central atom, that is also linear. And one thing, keep one thing in your mind, my dear student, please note it down, that if a molecule has no lone pair of electron, then its molecular geometry and electronic geometry both will be same. So in that case, both are linear. Angle will be 180 degree. And what are the common examples of this system? They are CO2, which has linear shape and 180 degree angle. Zinc chloride, all the compounds of zinc, whether they are chlorides, fluorides, hydrides, they will be included in this category. Mercuric chloride, all alkynes like ethyne, propyne, etc. All compounds of beryllium, beryllium hydride or beryllium chloride or beryllium fluoride, they will be considered in this category. And magnesium compounds, whether they are chloride, fluorides or hydrides, they will be having angle of 180 degree. So these are the common examples which are usually asked in the question papers. So you are required to memorize their angle, and that is basically 180 degree. Now, if we have sp2 hybridization, then the electronic geometry will always be trigonal planar. In case of sp2 hybridization, electronic geometry is always trigonal planar. Trigonal mean three-cornered and planar mean all the electron pairs and all the atoms will be in the same plane. Now there are two systems. The first is in which the central atom has three bonded atoms and all there are bond pairs around the central atom. Now look at this please. I have already mentioned that if a molecule has no lone pair of electron, it is a rule that its electronic geometry and molecular geometry will be same. So in this case, the electronic and molecular geometries both will be trigonal planar and the angle will be 120 degrees. Aluminium chloride, boron trifluoride, sulfur trioxide, these are some common examples. So next time whenever in the question paper the bond angle of SO3 is required, so that will be 120 degree, or the bond angle in BF3, that will be 120 degrees. So you are required to basically memorize the bond angles of the common examples that can be the part of your question paper. Now the similarly the phosgene COCl2, that will also be included in this, and all the carbonyl compounds like aldehydes and ketones, they have also bond angle of 120 degree. My dear students, the next case is in which there is one lone pair of electron and two bond pair of the electrons around the central atom. Now the lone pair gets involved. In that case, whenever the lone pair is there in a molecule, its electronic and molecular geometry will always be different. So let us first look at its electronic geometry, which involves the arrangement of lone pair and bond pair. This one is a bond pair, this one is another bond pair. So the arrangement of lone pair and bond pairs is again trigonal planar. So its electronic geometry will be trigonal planar. Now let us see the arrangement of atoms. It has two atoms attached. Now the arrangement of atoms is this one. It will be bent or angular, and because of the presence of lone pair, as I have already mentioned, that bond angle is inversely proportional to number of lone pair. There is one lone pair, so the bond angle will be less than 120 degree. And the common examples are SnCl2, PbCl2 and SO2. They all have bond angle less than 120 degree. The next is the sp3 hybridization, in which the electronic geometry is always tetrahedral non-coplanar. Tetrahedral mean it will be having four sides, and non-coplanar mean all the electronic pairs or atoms will not be present in the same plane. In this category, there are three cases. The first case is in which all are bond pairs and there is no lone pair of electron. So in that case, the electronic geometry and molecular geometry both will be same, and they will be tetrahedral non-coplanar. The angle will be 109.5 degree. And alkanes, carbon tetrachloride, carbon tetrafluoride, PbCl4, PbF4, and similarly stenic chloride SnCl4. These are the common examples of this system. So you are required to memorize that bond angle in all these compounds, that will be 109.5 degree, and their hybridization will be sp3. In the second case, dear students, there is one lone pair and three bond pair of the electrons. When the lone pair gets involved, then the electronic and molecular geometries, they become different. In that case, if we look at the electronic geometry first, ignoring the atoms, the electronic geometry is again the arrangement of bond pair and lone pair, that is again tetrahedral non-coplanar. But when you look at the arrangement of the atoms only, ignoring the lone pair, so arrangement of atoms, that will be trigonal mean three cornered, pyramidal mean it is just like a pyramid. So that will be trigonal pyramidal, and when the lone pair is there, the bond angle reduces, so that will be less than 109.5 degrees. In this system, there are very important two examples. One is the ammonia, in which you are required to memorize that the bond angle is 107.5 degree, and other is the fluoramine, in which the angle is 102.3 degree. My dear students, why there is variation of bond angle in these two? it has 107, it has 102. Why the fluoramines, they have lesser bond angle as compared to the ammonia? The mystery lies here. Bond angle in ammonia and NF3, central atom is same. What is different? That is the peripheral atom. In NF3, the peripheral atom is more electronegative. When it is more electronegative, the electronegativeness of peripheral atom is inversely related to bond angle, so its bond angle should be lesser. That's why the bond angle in NF3 is less as compared to NH3 due to greater electronegativity of the peripheral fluorine atoms as compared to the hydrogen atoms in ammonia. PCl3, chloramines, these are all examples in this system. Now the last one is in which there are two lone pair and two bond pair of the electrons. My dear students, in that case, because the number of lone pairs are even greater as compared to this case, so the bond angle will be even lesser than 109.5 degree. What will be the electronic geometry? Electronic geometry in one hybridization always remains same. If it is sp3, electronic geometry will always be tetrahedral non-coplanar. So in this case, again, the electronic geometry is tetrahedral non-coplanar. What is the arrangement of atoms now? Mean molecular geometry. That is basically, now you can see it is bent or angular, and the angle is 10 less than 109.5 degree in case of water, that is 104.5 degree. In case of H2S, that is nearly 92 degree. Why there is difference between water and H2S when they belong to the same system having two lone pair and two bond pair of the electrons? Again, look at this relation. Bond angle is directly proportional to electronegativity of central atom. In water, central atom is oxygen, which is more electronegative, so its bond angle will be higher. While in H2S, sulfur is the central atom, which is less electronegative, so its bond angle should be lesser, as the bond angle is directly proportional to the electronegativity of the central atom. Now let us discuss the next part of this lecture. Now the next system is DsP3 hybridization, in which the electronic geometry in all cases will be trigonal bipyramidal, but the molecular geometry, that will be different depending upon the number of the lone pairs in the molecule. Now my dear students, in case of this first system, as there are all 5 bond pair of the electrons, there is no lone pair of the electron. So in this system, the molecular and electronic geometry both will be trigonal bipyramidal, and the bond angles will be 120 degree C, 120 degree and 90 degree. And the common examples are PCl5 and PEF5. So you are required to memorize that the bond angle in PEF5 and PCl5 is 90 and 120 degree. The second one is in which there are 4 bond pairs and 1 lone pair of the electron. In that case, the electronic geometry, that will remain trigonal bipyramidal, but my dear students, the molecular geometry, that will change, and in that case the bond angles will be 120 degree C, 90 degree, 120 degree, 90 degree and 180 degree. And the molecular geometry in this case, that is called as seesaw geometry, just like the seesaw in the playgrounds. You have seen the seesaw. So its molecular geometry is seesaw, and the angle is 120, 90 and 180. The common examples are arsenic tetrafluoride, sulfur tetrafluoride, sulfur tetrachloride, and xenon dioxide difluoride, XCO2F2. So next time, whenever the bond angle of all these molecules is asked, you must have an idea that the bond angles are of 3 types: 120, 90 and 180 degree. Now next one is this one, in which there are 3 bond pair of electrons and 2 lone pair of electrons. This is called as T-shaped. You can see this is a T, and the angle will be 90 degree and 180 degree. Examples are Cl3F3 and XCF3 negative. In case if the D2sp3 hybridization is there, the electronic geometry will always be octahedral, and the molecular geometries will vary depending upon the number of lone pairs. In this case, all 6 are bond pair of the electrons, so the molecular and electronic geometry will be same, and that will be octahedral, and the angle will be 90 degree and 180 degree. Examples are sulfur tetrafluoride and molybdenum hexacarbonyl. And if there is 1 lone pair and 5 bond pair of the electrons, then the electronic geometry, again, that will remain the octahedral, but the molecular geometry will change. In that case, the angle will be 90 degree, and there will be example of boron tetrafluoride. That is basically, it is called as the square pyramidal shape. And the last one is in which there are two lone pairs and four bond pair of the electrons. The bond angle remains 90, that is the square planar shape, and in that the example is xenon tetrafluoride. So these are different types of hybridization with different shapes, but the main concept is number one, you should have an idea that there is difference between molecular geometry and electron pair geometry or electronic geometry. And secondly, you are required to memorize the bond angles in the different common examples that I have quoted in this lecture. Mostly the question they are asked from these examples, that what is the bond angle in the respective compound. So that was all about the bond angle. Next time we will come up with some new lecture. Till then, take care.